A few separate thunderstorms can sometimes join forces and become one huge, organized weather engine. That engine is called a Mesoscale Convective System, or MCS, and it can bring hours of heavy rain, damaging wind, lightning, and flash flooding. The story usually begins with warm, moist air near the ground, unstable air above it, and some form of lift. That lift might come from a front, a sea breeze, mountain ranges, or the cool outflow from earlier storms. An ordinary thunderstorm often rains itself out. Its rain-cooled downdraft falls into the same area where warm air is trying to rise, cutting off the storm's fuel supply. In an MCS, the storms avoid that quick collapse by organizing. Heavy rain produces cold, dense air that sinks to the ground and spreads out like a shallow wedge. This is the cold pool. Along its leading edge, called the gust front or outflow boundary, the cold air shoves underneath warm, humid air and forces it upwards. That lifting triggers fresh thunderstorm cells along the boundary. As nearby cold pools merge, many separate storms start feeding the same larger system. Wind shear is the next key ingredient. When winds change speed or direction with height, they tilt the rising updrafts away from the falling rain. That separation stops the downdraft from smothering the updraft, so the system can keep regenerating new storms. A mature MCS often has a fierce leading convective line. This is where the strongest updrafts, heaviest rainfall rates, most frequent lightning, and damaging straight-line wind gusts are found. Behind that line sits a broad trailing stratiform rain area. It may look less violent on radar, but it is a major part of the machine, spreading rain over a huge region for hours. Inside the stratiform region, falling precipitation evaporates into drier air and cools it. That heavier air sinks and helps pull a stream of air in from behind the system, called the rear inflow jet. As this jet descends, it can strengthen the cold pool and push the gust front forward. That creates a feedback loop. The cold pool lifts new air, new storms form, rain reinforces the cold pool, and the system keeps moving. Around the world, MCSs are major rain producers, especially in the tropics. Large-scale waves, monsoon troughs, low-level jets, and mountain ranges can all help organize them. In northern Australia, extreme heat and moisture from nearby seas make the wet season especially favourable. The famous Hector storm over the Tiwi Islands forms when sea breezes collide and force humid air upwards. Farther south, humid easterly winds and the Great Dividing Range can help organise storm clusters and squall lines over eastern Australia. These systems can deliver valuable summer rain, but they can also produce large hail, flash flooding, and destructive straight-line winds. A squall line is one type of MCS, arranged as a long, narrow band. A supercell is different. It is usually a single, highly organized storm with a rotating updraft. The key idea is that an MCS is not just one thunderstorm. It is a community of storms linked by outflow, wind shear, and shared circulation. When those ingredients line up, scattered cells can become a long-lived severe weather complex, and that is why forecasters watch boundaries, moisture, instability, and wind profiles so closely.